Hello teachers, welcome back to Chapter 4. We're going to talk about Section 4-2 today, prime and composite numbers. Students will be able to understand and explain the following. So we're going to talk about prime and composite numbers and define what that means, the number of divisors of any whole number, and we're also going to talk about the fundamental theorem of arithmetic. So let's start off talking about an example. Visually, the following rectangles represent the number 18. So think about 18 and how many ways you can express that as a product of factors. So we know we have 1 times 18. So the number 1 times the number itself, and that can be represented with one row with 18 blocks. What's another way that we can do that? Well, we know 2 times 9 equals 18, so we could represent that as a rectangular array with 2 rows of 9 blocks. And then that's not the only thing. We can do 3 times 6 to equal 18, which will include 3 rows with 6 blocks. Notice all of these examples have 18 blocks. So we're talking about a product of two numbers that gives us 18. So the number 18 has 6 positive divisors. Remember, we call those factors divisors. What's a divisor? If you remember, a divisor is a number that divides into another number with a 0 remainder. So 1, 2, 3, 6, 9, 18, all of those are divisors of 18. Can you think of any more? And you start going through the list, right? We looked at 1 and 2 and 3. Does 4 divide 18? And we know it doesn't because the remainder is not 0. Neither does 5. 6 is already on our list. And do we need to keep checking? You could keep going up, but as soon as you get to, you'll see what I mean, as soon as you get to another number on the list, when we did 3 times 6, we've got everything included on the list. We've checked everything, but we'll talk more about how you know when to quit checking. But let's mention something else. This is an interesting list worth discussing. Notice we have a list of numbers across the top. 1, 2, 3, 4, 5, 6, 7, 8, 9. That is the number of positive divisors. See, the problem we just did, here's what we're looking at. For instance, 18, how many divisors does it have? Notice I've got it scooted over on the page. Don't worry about that. But we've got 1, 2, 3, 4, 5, 6 divisors. So if I go back to my chart, under 6, you'll notice the number 18. That's what we're doing. We're counting how many divisors a certain number has. So what's in your list is the actual number. So what we're saying here in the first column is 1 has 1 divisor. The number 2, 3, 5, 7, 11, each of those numbers has 2 divisors. That's going to be pretty significant. We're going to talk about what all these numbers have in common in just a minute. But all of these numbers, they have only 2 divisors. Think of a number that has 3 divisors. Well, how about 4, 9, 25? 4, 9, and 25 each have 3 divisors. Interesting. What's going on with these do you recognize a pattern there? Only 3 divisors means, for instance, 25. Let's take a look at the number 25. 25, the divisors, the set 1 and 5 and 25, because 5 times 5 gives you 25. 3 divisors is going to represent perfect squares, right? 2 times 2 is 4, 3 times 3 is 9, 5 times 5 is 25. That's an interesting list. So whenever you only have 3 divisors, it looks like, without proof, it looks like it's going to be a perfect square number. But if you think about it, it makes perfectly good sense because every number has a divisor of 1 in itself. So you have at least 2 for every number except 1, right? Because 1 in itself is just the number 1. So every number bigger than 1 has at least 2 positive divisors. But when you get to 3 positive divisors, it looks like you're looking at perfect square numbers, but not all of them. Right, for instance, 36. What about 36? Well, 36 has 6 and 1 and 36, but other numbers go into 36 also, like 9 and 4. So, you're not talking about every perfect square, just some. Let me write this in here. That's just going to be some perfect squares. I'm just going to put n squared to represent perfect squares. Well, what about 4 divisors? So if you look at the number 6, for instance, we know 1 times 6, that's 2 of them, but also 2 times 3. And you would count, if you calculated the divisors for every one of these numbers, it would have 4. 16 has 5, which is very interesting. Notice it's a perfect square also, right? That's something to think about. 18, we looked at 18, 6 divisors. So do 12, 20, 28, 32. Are these the only numbers with 6 divisors? Well, no. We just went up to 37, and that's it. That's the highest number we're taking a look at. Nothing with 7 divisors. Very interesting. Because an odd number of divisors is an interesting situation, isn't it? 8 divisors. You could list all the divisors for 24, all the divisors for 30. If you added them up or counted them up, you would have 8. And look at here again. Look at that. Okay? All the odd numbered divisors have perfect squares in the list. Why do you think that would be? Very interesting, this list. Something to think about. All the odd numbered divisors, okay, you're counting divisors, right? Keep that in mind. That's what this chart is. So the number 4 has 3 divisors. The number 16 has 5 divisors. The number 36 has 9 divisors. To get an odd number of divisors, you're going to have a perfect square, because divisors show up in pairs, right? So for instance, 18, if I go back and look at 18, well, listen, let's just move the list for 18. So the divisors of 18, remember, were 1 and 18, 2 and 9, 3 and 6. Okay? Notice these show up in pairs, 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 correct? All right, well, to get an odd number of divisors, you're going to have a perfect square, because 5 is 5 times 5, but you only list it one time because this is a set. So a very interesting thing comes from this list. Now the textbook points out that this list, like we did already, has exactly 2 positive divisors. Those guys are called prime numbers. That is the definition of a prime number, that you only have 2 positive divisors, and they are going to be 1 and the number itself. And all of those are listed prime numbers. On the other hand, all these other guys, if you have more than 2 divisors, then you are called a composite number. Here we go. So real big at the top there. Any whole number that has more than 2 positive divisors is what we call a composite number. So it has divisors other than 1 in itself. All right. And then when we talk about prime and composite numbers, the number 1 has only 1 positive factor. Very important here in red, and I'm going to highlight it also. 1 is neither considered prime nor composite. Okay, so when you talk about the number 1, and we're talking about whole numbers, or in this case, just counting numbers, okay, then you're dealing with 1. It's neither prime nor composite. So that brings me to a definition. A prime number is any positive integer with exactly 2 distinct positive factors. Notice this definition extended to integer, but we haven't had the integer conversation in this class yet, so you could exchange that with whole numbers. So any whole numbers that have exactly 2 distinct, which means they're different, right, positive divisors, then that is considered a prime number. That will extend to integers when we get to integers. A composite number, on the other hand, is any integer greater than 1 that has a positive factor other than 1 in itself. So that means it would have 3 or more divisors. Now for this problem, we are supposed to show that 1564 is either prime or composite. This actually says show that the following numbers are composite. So that's our goal. We want to show that this is composite, which means something other than 1 in itself divides 1,564. So my question to you is, what divides, let me write this down, what divides, or what is the divisor of 1,564? I bet you recognized right off the bat that 1,564 is an even number because we have 4 in the units position. So I could write proper notation that 2 divides 1,564. Therefore, there I go with my dots again, therefore 1,564 is composite. Now I have that typed up for you. There it is. Since 2 divides 4, 1,564 is divisible by 2 and is therefore composite. Now pause it. I want you to do the same thing, not the same work of course, but the same idea to 2,781. Now the real question is this number prime, where it only has 2 factors, 1 and the number 2,781, or is it composite? Notice the directions though say, show that the following numbers are composite. So we already know ahead of time it's composite, but sometimes you don't know ahead of time. You just have to do the work. Now, what do you know? First of all, it's not an even number, right? Because that means it's not divisible by 2 because we have a 1 in the units position. So the first result is not going to work this time. How about we check by 3? Do you remember the divisibility test for 3? We add 2 plus 7 plus 8 plus 1. The only time you add a sum of numbers to figure out if it is divisible by something is for 3 or 9, right? So if your sum is divisible by 3, then your whole number is divisible by 3. If your sum is divisible by 9, the whole number is divisible by 9. And then we have that weird trick for 11 where you sum every other number and subtract. So we're summing 2 plus 7 is 9. 9 plus 8 is 17, plus 1 more is 18. Check it out. 3 divides 18, therefore 3 divides 2,781. And because we know that something other than 1 in itself divides 2,781, that means that this is a composite number. And again, I have this typed up for you. Again, since 3 divides the sum of your digits, that means 2,781 is divisible by 3 and is composite. Now let's try this again. So again, pause it for me. Determine whether 1,001 is prime or composite. Remember the directions, it really said it was composite. So you're tasked with finding a divisor of 1,001, no and, right? No and unless you have a decimal place. If 1,001 that is divisible by anything other than 1 in itself. And then how about go ahead and do D as well. All right, you promised me you pause it and work these out. Now 1,001 might stump you a little bit. It's certainly not divisible by 2 or any even number because it's not even. So you check 3, the sum of the digits, 1 plus 0 plus 0 plus 1 is 2. It's not divisible by 3. It's also not divisible by 9, right? Certainly not divisible by 4, again, because we decided it's not even. 5 is out. 7, how would you check 7? Well, 7, you just divide. So you could do long division, 7 divided into, because we're going to assume you don't have a calculator right now, right? 7 divided into 1,001. If you're impatient, you pull out a calculator. I've certainly done it. But the remainder is not 0. Not equal to 0 right here. So 7 doesn't divide. 9 doesn't. We've already talked about why. 10 doesn't. Maybe we should check 11. Remember the cool trick for 11 is that you add up the digits that are in the 10 to an even power position. So here and here. Turns out it's every other digit. So I add 1 plus 0. Okay, so that would be 1 plus 0, the ones I have highlighted. Subtract out the other two, the ones not highlighted, 0 plus 1. Well, that gives me 1 minus 1, which is 0. Does 11 divide 0? Sure does, right? You can't do 0 divides 11, right? But 11 divides 0. In other words, 0 divided by 11 is 0. If 11 divides that sum, then you know 11 divides your number. And if 11 divides 1001, that means it's composite. All right? What about the next one? Okay, so we're trying to show that 3 times 5 times 7 times 11 times 13 plus 1 is a composite number. That's interesting. Now, if you paused and tried to work this out, you might have bailed on me and pulled out your calculator, right? 3 times 5 times 7 times 11 times 13. I'm going to do that because it is a possibility that you did that. So stand by while I multiply this out. But then I'm going to tell you a different way you could think about this. Okay, it's big. So 15,015. So this, pen error, there we go, is equal to 15,015 plus 1. So that is 15,016. Now, what do you know about 15,016? It is an even number. So 2 divides 15,016, and therefore that number is composite. Now, here's something I want you to think about. All of these numbers are odd. And you may have noticed this, you may have realized this already. But whenever you multiply a product of odd numbers, the answer is always an odd number. So I knew before I multiplied this in my calculator that this is odd. If you take an odd number and you add 1 to it, it turns it into an even number, right? And that tells me right off the bat this is composite because 2 divides every even number. Neat trick, don't you think? Oh, yeah, typed up. Here you go. The product of odd numbers is odd. So 3 times 5 times 7 times 11 times 13 is odd. We don't even care how big it is because it's big. It's odd. When you add 1 to an odd number, the sum is even. All even numbers are divisible by 2, and all even numbers except 2 are composite. Remember, 2 is prime. Every other even number is composite because it is divisible by 2. All right, so let's talk about prime factorization. Composite numbers can be expressed as products of 2 or more whole numbers greater than 1. We know this. Each expression of a number as a product of factors is a factorization. A factorization containing only prime numbers is what we call a prime factorization. So every single whole number can be written as a product of prime numbers. And that, again, that's what we call prime factorization. And we have this fundamental theorem of arithmetic. It's also called the unique factorization theorem. So those terms would be used interchangeably. Each composite number can be written as a product of primes in one and only one way, except for the order of the prime factors in the product. So, for instance, we could write 18 as 2 times 3 times 3. You will also see that listed as 2 times 3 to the second power since we have 2 3's. So that is 18. You could check it. If I come over here to the right just to check my work, that would be 2 times, we know 3 squared is 9, and 2 times 9 is 18. So this is what we call the prime factorization of 18. And every single whole number can be written as a product of primes unless it's already prime, and that is just the prime number itself, right? Okay, to find the prime factorization of a composite number, rewrite the number as a product of 2 smaller numbers. Okay, if these smaller numbers are both prime, you're finished. If either is not prime, then rewrite it as a product of smaller natural numbers and continue until all the factors are prime. So this is the how-to, and really what this is called is a factor tree. So when I'm speaking of this, I'm really talking about a factor tree. I promise you have done it before. It's one of my favorite things to do in just number theory. So here we go, 84. Let's do a factor tree for 84. So in your mind, imagine 2 numbers, any 2 numbers that multiply to be 84. and I'm just going to branch out. Now the numbers that occurred to me are 12 times 7, but you might have thought of something else, but I'm thinking 12 times 7. And then 7, if you'll notice, is prime. I tend to circle mine when I get to an end of the branch, but 12 is not a prime number. So I come down, and 12 we could write as 4 times 3. Is it okay if you write it as 2 times 6? Of course it is. 3 is a prime number, and then 4 can be broken down as 2 times 2. And both of these twos are prime numbers. So I could write 84 as 2 times 2 times 3 times 7. Simplified would be 2 squared times 3 times 7. And this is the unique prime factorization of 84. Is that the only way to get there? It's not. We could have done this a completely different way. Let's do it. So let's take 84 again over here on the right. So 84. What if you didn't think of it as 12 times 7? What if you thought about it as, say, 2 times? Because we know 84 is an even number, right? So it's divisible by 2, and it's 2 times 42. Okay, 2 is prime. 42, maybe the first thing you thought about was 2 times 21. Or maybe not. You probably thought about 6 times 7, but let's go with 2 times 21. 2 is prime. 21 could be factored further into 3 times 7. 3 is prime, 7 is prime, but if you'll notice your list, it's identical to what you got before. You have 2 2s, a 3, and a 7, and if you multiply this back on your calculator, or you could do this in your head, 2 squared is 4, 4 times 3 is 12, 12 times 7 is 84. Not only that, you can multiply these back up. You know, if you had the answers down here, you could say this 2 times this 2 is 4. This 4 times this 3 is 12, and this 12 times this 7 is 84. You could build your way back up if you had the results. Now I've got a second number, notice how it's scooted over on the screen. You'll see why in just a minute, so I can fit 84 and 4095 results on the same screen. How about you pause it? You do a factor tree for 495 to make sure you feel comfortable with this, okay? Come back and we'll compare answers. Now, you don't have to do it the same way I do. I'm thinking about 495 is something times 5. Now, if I'm not using my calculator, and I encourage you highly not to use your calculator, this is what we need to do, right? We're going to use that standard algorithm for long division. How many 5s fit into 400 is really what you're thinking, but we can scoot over to the 49, and we know that 9 times 5 is 45. And then we subtract, don't forget, 4, and then you bring down the next position. 5 goes into 45. 9 times 5 is 45, with a remainder of 0. So we could say 5 times 99 is 495. 5 is a prime number. Why? Because only 5 times 1 gives you 5. No other divisors. All right, 99 breaks down into 9 times 11. 11 is a prime number. 9's not, right? 9 breaks down into 3 times 3. And now I have all my primes. So notice if I write these in ascending order, this is 3 to the second power because I have 2 of them, times the next larger number is 5 times 11. Most of the homework wants you to write these in ascending order. You could check it. 3 squared is 9 times 5 is 45. And then you multiply 45 times 11, and you should get 495. Now, here it is all typed up fancy for you. If you'll notice, those are the same results that we got before. You may not recall. The factoring looks very similar for 495. 84, they did completely different than I did it, but maybe you did 84 that way. I've got another one for you. Why don't you pause it and try it? All right, so I'm going to break down 260. And here's what I notice. Because that ends in a 0, this is divisible by 10, right? So I'm going to say this is 26 times 10. Then 26, what does it break down? It's certainly not prime because it's an even number. Maybe 2 times 13, and maybe that's your only option, right? Because 2 is prime and 13 is prime. There are no other factors of 26, other than 1 times 26. And you don't want to use 1 because that's not going to get you anywhere. You need these as prime numbers. 1 is not a prime number. 10 I can break down into 2 times 5. Those are both ends of branches also. Notice I've got 2 2's, so that's 2 squared, times the next largest prime is 5 times 13. Again, how do you check yourself? Hey, just multiply it back out. 2 squared is 4. 4 times 5 is 20. 20 times 13 is 260. Now here we go, pointing out that there's more than one way to get the prime factorization. On the other hand, the result is the same every time. So it's okay if you and your buddy get there 2 different ways. Notice both of these have 2 2's, a 5, and a 13. There we go, 2 2's, a 5, and a 13. We can also determine the prime factorization by dividing with the least prime, 2 if possible. If not, we try the next larger prime as a divisor. Once we find a prime that divides the number, we continue by finding smallest prime that divides that quotient. I have now seen that this has a special name, but I kind of call it the box method for prime factorization. But it's just different than doing a factor tree, but it works just the same. It keeps you a little bit more organized on the page, but this is entirely up to you. And I think students need both options. They just need both options. Find the prime factorization of 260 by dividing with the least prime. So here's what we can do. You write the number 260, and you just make a little box. What divides into 260? You want to pick the smallest prime number. Does 2 divide into 260? Sure it does. It goes 130 times. Does 2 divide into 130? Sure it does. It goes into it how many times? 65. If you did not see that, just scoot over and do long division over to the side. Now, 65 does not divide by 2, right? Because it's an odd number. Only even numbers are divisible by 2. But I do see that 5 goes in there, right? Now, I probably could have checked, you know what? I should have checked 3. If we're going to do this least prime method, I'm trying to erase y'all and it won't let me erase. There it goes. The least prime method. Is 65 divisible by 3? Well, you would add the digits. 6 plus 5 is 11. 11 divisible by 3? No, it's not. So I did just fine by putting a 5 here. But we should check all the prime numbers. Now, 65 does divide by 5. And it divides by 5 13 times. Okay. What do you know about 13? It's prime. So 13 goes into 13 the one time. Which means my prime factorization is 2 times 2 times 5 times 13. There you go. So 2 times 2 times 5 times 13. There's a couple of ways to do this. Again, I've always called this the box method. So notice this one looks the one on the left looks very similar to what we just did. The one on the right is slightly more organized, but notice it's exactly the same result. So you can organize this however you feel more comfortable. I really like just the 2-column table over to the right. I'm a big fan of that. Now, because I'm swiftly approaching the 30-minute mark, I'm going to go ahead and shut this down. We're going to come back for part 2.